feel that I will give my best, you also give your best, right? Ask your questions and I'll be attentive in the class and ensure that we both get like something out of this session, right? I feel happy about teaching that, yes, you guys were involved in the session, cleared all your doubts, and I was also able to deliver and clear your doubts, right? And at the end, obviously, it should reflect in the feedback. It's not reflecting here, right? It looks like the doubts were not cleared. So I will request you guys, it's obvious that everyone will have doubt. This is machine learning. We are learning it for the first time. You will have doubts, but request you to clear it, right? And the same thing should reflect in this rating as well, guys. Please, I request you. Okay. So is it clear, guys? Guys, whatever I said, is it clear? Yeah. Request you guys. Okay. Okay. So where were we? I will connect. Okay, connected. Before we proceed, any questions from previous session, guys? Any questions from previous session? Please let me know. Any questions, guys? Yes or no? If it's a no, then write no, no problem. Yeah, sure. This is what I'm asking for, Satish. Yeah. So if you have any questions, do ask, right? Obviously, I will also ask if you have any doubts or something. But yeah, do ask your doubts. So yes, Satish, I'll give a recap. But Praveen, you first asked it. With the use case you said, right? Yes, definitely. Definitely we can come up with a use case. Yes. So what we are doing is, how we are going to do it is, Praveen, in this particular sheet, when we complete it, we will have already done use cases. Okay. If you see, I already uploaded these CSV file and Excel file, right? This I uploaded for the use cases only. So in case of linear regression, right? Housing prices is an absolute great use case. Then for non-linear, right? For non-linear, position and salary is something which we can use the non-linear or the polynomial stuff to predict, right? And diabetes data set is there. We will see. Okay, we'll see every each of these. And yes, so linear regression in itself is hello world of machine learning, you know. So accordingly, the use case that we are doing is also the same. Okay. Yes, we can definitely try any other use case, but what what's important is to understand the concept. As we move forward, definitely the use cases are going to get better, right? But from the broader perspective, let's understand this with a simpler use case. And definitely, mark my words, once we grab all these things, we can go ahead and use a complicated use case as well. Now, where we are going to use it, if you know, we are going to build a project, right? So we have a specific class for project as well. So there we can see. Now, Praveen, what I wanted to know is, you are asking me to give you a use case, like explain you how it works, a good use case, or you want me to do like this coding thing? What do you want right now? If you want me to use a different use case and code it, then no, we will not be doing it as of now. We'll do it later. But if you want me to explain a use case where these, like a complex use case where we can use linear regression and non-linear regression, yeah, yes, okay, okay, certainly we can do it. Are there any questions as well? Any other questions? Please mention that question, and we will take all in say next 15-20 minutes. Please type. Any other things, guys? Guys, any other questions? Please write all the questions in the chat box in the meantime. If no, then we will continue with this, and after this, I will give a recap and we will proceed. Okay. Can we do code collaborate with you and learn this weekend to build some coding confidence? Yeah, I'm asking you guys to do it along. No, these sheets are already with you guys. Okay. Okay. So let me explain a complex use case, right? So a problem statement I will give you. A health insurance company is there. It wants to predict the medical costs of patient based on various factors, right? Such as, let's say, age, BMI. What else is there? What can be other medical factors, guys? Chronic disease, lifestyle choices, smoking habit. What else you can add? Okay. The goal is to build an accurate pricing model for insurance premium. Okay. So whenever a customer is coming with the requirement that they want an insurance and okay, so I want an insurance for let's say 1 crore, 1 CR, right? And I will be mentioning all my details like the age, BMI, smoking habits, chronic disease, lifestyle choices, and everything. So you guys must have booked a insurance for yourself. So there you might have come across this, right? So according to the choices you give, the system gives you a premium for the insurance plan. For example, if you smoke, right, then the premium will be more. If you are having some existing chronic disease, the premium will be more. So mm, here, what do you? No, no, no. I'm not sharing. I'm just speaking. There is nothing to share, right? You just need to understand. So, guys, what do you think? Uh, these are the factors like age, BMI, smoking habit, chronic disease, lifestyle choices. These, right? These are all the factors that contribute to the premium, right? So, what is the target value here? Can anyone comment? Anyone can comment. What is the target? Yeah, the target value is the premium. And what are the parameters? Exactly, guys. Yeah. So, it can be two things. Either we apply linear regression to this, or we apply non-linear regression to it, right? What do you think? Right? What do you think at this point before I actually share my screen and start explaining you stuffs? What do you think should be applied here? Linear or non-linear? We can apply both, but according to me, I believe non-linear fits perfect here. How? Let's see. So I will share my screen now, and we will understand something. Okay. Non-linear has too many inputs and factor influence. Yeah, exactly. No, it's not non-linear. Uh, Guys, you are able to see the screen, right? Let me increase the brightness. Okay. So, hmm, if it is a linear, first let us try with linear. medical cost or premium can be written as like this. Let's say beta 0 plus beta 1 dot age plus beta 2 dot BMI plus beta 3 into smoking plus beta 4 into chronic diseases plus, let us consider a error term epsilon. It will come later. So here what's happening, guys? Here we are taking a linear relationship for each factor. Okay. Now, if you want, you can proceed with linear regression, no problem. And if you want, you can also proceed with non-linear. What I will do is I will write the equation for non-linear also. Yes, they are all parameters or variables. Now I will write a equation for non-linear also. You guys tell me which one looks more promising. So if a polynomial or non-linear equation we would like to write, it would look something like equals to beta 0 plus beta 1 into h plus beta 2 into uh, let's say age square. So here what's happening? It might be a case that age is coming twice. It might be a case. Plus, let's say beta 3 into BMI to the power q plus beta 5 into smoking, right? So whatever, you can use whatever, no problem. Now tell me, which particular equation looks more promising from an insurance company point of view? No, if there are multiple, here as in S. No, 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 no. Here it would like look like this. Age would be x1, BMI would be x2, smoking would be x3, like this. Okay. So x is the variable or x-axis, but we are taking multiple scenarios here. Okay. Multiple parameters here. Got it, guys? Now, here, as each parameter is having a linear relationship with the target value, it is called linear regression. But here, in this case, a parameter is having, even one parameter is having a non-linear relationship with the target value. We call it a non-linear or a polynomial regression. Is it clear till now? Guys, is it clear till now? Now, now, what do you think will we choose, right? From the insurance company point of view, what will we do? We will test this for a wide variety of records, right? Across multiple age groups, across multiple BMI groups, across smoking or non-smoking candidates, across candidates for chronic diseases, various chronic diseases, right? So we will test it and we will see how the premium is varying. And accordingly, we will charge the premium, right? So it's not that we already know that this is going to be a linear or a non-linear regression, right? We will have to do both and see in which the data fits better, right? In which it is able to predict better, and we will take that. Okay. So this is from the theory point of view. Now, obviously, when we do it, we will explore more and more. So I will get this type of data set. I don't have it right now. Also, just getting a data set and working on it does not would not be appropriate for a scheduled class like this, right? So I will have to get the data set, work on it myself, see what are the output, and then we can plan to include it in our curriculum, right, guys? So obviously, I will include it tomorrow. I will find some 15-minute slot for this at the end of the class. I will have done the coding beforehand and I will show it how it works both for linear and non-linear. So Praveen, will it work? And others, will it work that way? Before that, please tell me if it's clear from the theory point of view. It's clear, right? Perfect. Awesome. And I really like this, guys, that you asked, right? If you have any questions, do ask. I am more than happy to take an extension if we are falling behind. No worries on that. Okay. Is it clear? I am ready to take it a bit slow. And if we fall short of time, I am happy to take an extension of one class. No problem. Okay. Everyone is fine with it. But I am not going to run fast and like so that you don't understand even one thing. I won't accept that. So everyone needs to understand everything while we proceed. And the slowest learner in the batch will decide the pace for this class. Okay. So our aim is to hasten our pace, but we have to ensure that we understand everything. That's it. Okay, we will proceed now. It will, I will run it all. Okay, it will give some error in the runtime. I will keep fixing it and then we will proceed. Let me get the, so it is read excel housing.xlsx key, hello, housing.csv. Runtime run all. Okay, so I hope no errors now. Everything ran fine. Let me check the last sheet. Yes, everything ran fine, I believe. Where were we? We covered this, no? Polynomial. We covered this as well, cross-val. We'll start from cross-validation today, right, guys? So basically, cross-validation is a technique that evaluates the model performance by dividing the data into multiple folds. Okay. What it does is, suppose you have 1,000 rows in your data. Suppose you have 1,000 rows in your data. Okay. What will we do is, we will randomly select 100 rows for one set. So if we randomly select 100 rows for one set and create 10 sets out of it. Okay. So from overall 1,000 records, one set 100 rows or 100 records. So total 10 sets. Everyone is okay with it? Okay. I was trying to see if you guys are able to catch it while I speak only. That's not a great idea. Better I share my iPad and show it you. Okay. One requirement, special requirement for you guys is, towards you guys is, do not skip a single word, whatever I'm explaining. Okay. Because if you skip even 10 seconds of it, you will fall short. You will like, then in order to explain you, I'll have to repeat the whole thing again. Okay. So that's a request from my end. Suppose you have a record where you have 1,000 rows. I want to create 10 sets out of it. So what will happen? One set will have 100 rows. So the 10th set will also have 100 rows. So each set is having 100 rows. Okay. Now what's happening is, out of this, we will do it in this manner. There is no test train split here. This 9 set of data we will use for training the model, and this one set we will use for testing the model. Okay. So the number of times we will do this. For example, here we have done 10-fold, right? Created 10 sets. So the number of times we do this is known as k-fold, where k equals to number of times we create the sample or the subset. Got it? Till now, is it clear, everyone? What is the need of cross-validation? Why we are doing this? We are doing this to improve the performance of the model. Who decides 9:1? This is an industry accepted pattern. Okay. This is how, like, these are all PhD level research that was done. Okay. And based on that, we have come to the conclusion that, like, k-1 fold we will use for training, and yeah, one fold we can use for testing. What will happen is, you imagine, okay, If you are having 10 folds and you are using 8 plus 2, like 8 for training and 2 for testing, what will happen? There is a chance that you will get in during testing or during validation, you might get known data or uh, like similar data to what you have trained the model. So in order to Saha, wait, I will see this message. Okay, let me explain. So in order to ensure that we are testing the model performance on unseen data, we minimize the testing set. So if it is testing or validation set, we try to minimize. So here it's one only. Got it, Sina? Saha is asking, I think we can even, no, anything, k minus 1, you can do 100 also. So the training set will be 99 and testing set will be 1. Okay, it's always k minus 1 for training and 1 for testing to make sure that the testing data is unseen. Now Saha is saying, I think we can even submit a paper we have if we have a different ratio, as this field is still under. Yes, if you can find something more efficient, obviously you can. K is given as parameter. No, K is not given. Acha, that way in coding you are saying, right, Sheena? While we yes, K is given as a parameter, how many folds you want. Like if we give like 1,000 folds, then what will happen? The data will get overtrained. You agree, Sheena? We have seen that, right? Bias variance trade-off. So it will get overtrained, which we don't want. So we have to maintain a balance. That's it. Okay. Now, one important, I did not explain it till the end. Let me explain it. Now there is one special thing which I need to add here. What happened here, guys? Out of 1,000 rows, I created 10 sets, right? What I'm doing, I am, guys, please notice, I am using 9 sets for training and 1 set for testing or validating. Okay. This is one fold. Now, suppose you do this 10 times. You do this 10 times. If you do this 10 times, then what will happen? Each set of data at the end of 10th fold validation will have been tested. What I mean to say is, oh, what I shared, no? Okay, let me explain again. Suppose we have 1,000 rows, right? So we create 10 sets out of it. 10 sets mean 100 rows per set. What we are doing is, Prashant, are you able to follow from here? Prashant? Yeah. So 1,000 rows are there, 10 sets. What we do is we use 9 sets for training and 1 set for testing. Okay. Now, suppose if we repeat this exercise 10 times, what will happen? We will have used all 10 sets for testing. It means at the end, each data row or each data point in my data set has been part of testing. You agree? Everyone agrees or not? Yeah. So we come across a scenario or we come across a process where we can create the data sets in such a way that each data point can be used as a testing set or a validation set, ensuring it is unknown or unseen to the training data. So what happens is, if I will try to make it more clear, suppose first set to 10th set is the data. What we are doing is, every time we are taking 9 set for training and 1 set for testing. Okay. Consider, and we are doing this how many times? K fold times. So 10, if 10 is the number of sets, we will do this for 10 times. So suppose first time, what happened? First set to 9th set is my training data. 10th set is testing. Similarly, second time or second fold, second to 10th set is training and first set is testing. Similarly, at the end or the 10th time, what will happen? first, second, dot, 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 10th set will be my training data, and the 9th set will be my testing, right? So as a result, what's happening is every time in each fold, I am creating a data set where the training is done on like a huge amount of data, and the testing set is a small data set which is unknown to that model for that fold, right? And eventually at the end, we are making sure that all 1,000 rows of data goes through scrutiny, goes through a validation set or a testing set in the model. So if you can build a model where each data point has been trained and tested as well, it gives you a very good performance. Yes, Nisha, whatever it is, right? So at the end of 10 folds, each set will have been gone through the testing set. That's what I was saying. Now, Gundriti is saying, but looking at it from another other end, it also means the model is being trained on every data point too. Don't that lead to overfitting? No, it won't lead to overfitting. Why? The reason is, everything that we are doing is random. Okay. So there are chances that all these 1,000 rows of data will be through testing, but not sure, because it's not that if I'm creating 10 sets of data, all 1,000 rows are covered in those. These are all random, right? So in the second set also, uh, there might be a case that we have data from the first set in the second set as well, right? Everything is random. And no, it won't lead to overfitting. We are making our model robust this way, that different types of data we are preparing it for. Okay. What happens is, instead of making our model overfitting, we are making it robust. How? Because we are not allowing it to get tested or trained on all forms, like all the data in a single fold. No, we are allowing it to get tested in multiple folds, and each time the data set is different. So since it's being trained multiple times, it's learning every time. It's not that it's getting trained one time on a huge data. No, it's getting trained multiple times. Okay. So basically all data going for testing and training. That's the ideal case, but randomly, like what we have seen is, so basically all data going for training and testing, right? Uh, no, Sri Kumar, there can be options for it. What are you selecting the random state? If random state is 0, it means we are not selecting the data like randomly at all. So all the data will go. But if random state is high, let's say 42, 98, something, then it's so random that we don't know if every data is gone through testing and training or not. Now, Sina is saying CV is done on complete data set or after splitting training. So Sina, generally, this concept we are studying is for the entire data set, but we don't apply it in industry standard like this. We do this as part of training data set only. The testing data set or the validation data set that's been kept is used once the model is created. Okay. So in industry, CV is done after splitting training and testing data set. Okay. Praveen is asking, okay, got it. But same data goes more than once in that case. But more than once means multiple folds. Okay. So yeah, it actually improves the model performance. Select what data is interesting. Exactly. As much we iterate, it basically gives a feedback to the model how much more to learn and all. So it basically does not overfit. That's the best part. Okay. So I hope the cross-validation theory part is understood. Now, what is the pros is it provides a more accurate estimate for model performance. And what is the con? The con is, if the data set is huge already, then it is computationally intensive. So this k-fold cross-validation that we do is actually done on data sets where the number of records is low. If we already have a huge data set, there is no requirement for cross-validation techniques. Yes, that is what we do in industry, right? Here, we can do anything for understanding the concept, but when we will actually implement cross-validation, we will do it on training data only. So we would not require a test print of our data. That is, I mentioned, right? I mentioned you that the technique k-fold cross-validation does not need any splitting. But for us, we want to select or we want to create a better model. So for creating a better model, we use k-fold cross-validation on training data only. And once the model is created, we will still need some data for validating the model, right? So from where will that data come? You got my point, right? So for that, we will need that testing data to be kept separately, such that our model has never seen it. Never, even during testing or even during training, using cross validation, that model has not seen the data. Then only we will see, right? We will understand that if the model is actually that much robust or not. You got it, everyone? Everyone? Yep. I am liking, guys, these questions. Like, you are making me happy. Any question? Keep firing the questions, guys. Is the validation done for every data set for which we are checking if the model is best fit? Is the validation done for every data set? No, validation. You need to be more clear. What are you talking about? Cross for k-fold cross validation you are talking, or you are talking about testing? Okay. Hmm. Every data set for which we are checking if the model is a best fit. Every data set. What do you mean by that? There is only one data set we are working on, right? So in that particular data set, there will be subsets. So are you talking about subset? Every subset if the validation is done? Is that the question? No. Then, okay, you are asking, like suppose there are 10 data sets on which we are building a model, right? Different data set, say housing data set, say medical data set. So if that k-fold cross validation is required on everything, is that the question? Okay, not actually necessary. This is a concept we are learning, right? At the end, you will have so many tools, right? Suppose you are playing a cricket match, you have 10 bowlers in your team. Apart from the keeper, everyone is a bowler. Will you bowl every bowler in the match? No, right? You will bowl them according to the situation and the requirement. Hai na? So here also same. Depending upon the requirement, if it's needed or not, we will understand that. Okay, once we start working on data set, we will know. We are still learning. Let's give 3-4 sessions. Okay, in 3 or 4 sessions, you will understand what to use, where to use. Right now we are learning what is this, where to use, what to use, how to use. It will come later, don't worry. Hmm. Okay, now guys, I want you to read this and tell me what it means, please guys. It's very easy to understand, very easy. You guys now tell me, what is this? Stratified k-fold cross validation. Mhm. To avoid biasing equal and all type of class count in data set. Let's try to make it more specific. It's a bit generic, still generic, Vijay. Let's add 1 or 2 more data, 1 or 2 more keywords, and it will be perfect. Okay, so then, mm, 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 mm. See, whatever we studied in k-fold cross validation, it is also the same. Just one difference. What is that? Saha is giving the right answer. Okay, let me tell you. Suppose in k-fold cross validation, what were we doing? We were marking or making the samples or sets totally randomly, right? So suppose in the 1,000 rows we have, I saw someone gave examples of different data, like different classes, right? How do we identify different classes? We don't. Python is well smart, very smart to do that. We don't need to identify. Okay, don't worry. So suppose there are 1,000 rows. There is one class called these rows is a fruit. Okay, so let's say name, fruit name. So if we do the count, apple is having, let's say, 30%, orange is having 30%, banana is having 10%, sorry, 10%, and grapes is having 30, 30, 60, 70, 80, 90, 20%, and pineapple is having 10%. Now, if we were making the sets random in a random manner, can it be a possibility? So if apple is 30% means 300 count, here also 300 count, here 10, 100 count, here 200 count, and here 100 count, right? So overall it goes to 1,000. So when we were making 10 sets, right? Can it be the case that first set will have 90 apple, 1 orange, 9 banana, 0 grape, and 0 pineapple? And all the sets are like this only, totally imbalanced. Can it be a case? You agree, right? This can happen when we are doing it randomly. So for the same case, we take stratified k-fold. where during making, uh, while making the subsets, we ensure that, let's say the first set will have 3 or 30 apple, 10 orange, 20 banana, right? Such that the ratio is the same. Got it? That's the only addition to normal k-fold cross validation. Stratified k-fold cross validation has this addition. What? That the different classes are in same proportion. Everyone got it? Everyone? Specific data set. Yes, yes, yes. So what is the pros for it? The pros is more reliable performance for imbalanced data set, right? And what is the con? Obviously computationally intensive, like huge computing power would be required to perform this, right? If you do it on Google Colab, this cross validation, and if it is a tenfold cross validation, you will see how much time it takes. Okay. Now we will proceed to build a linear regression model and try to perform analysis on it, evaluate it using, let's say, k-fold cross validation, stratified k-fold cross validation, leave one out k-fold cross validation, and so on. Okay. So we will be using this housing dataset here. If you look at this, how the housing dataset looks like is we have information like latitude, longitude, median age of the house, right? Total rooms in the house, total bedrooms, population, household, median income, and median house value. So what it shows is at this particular latitude and longitude, there might be multiple houses. I will explain when we go there, leave one out. Okay. It's part of k-fold cross validation itself, where we intentionally leave one or leave two or leave n out. We do not train on everything to make it more uh, mixed up. Okay. Yes, yes, yes. I will explain when we are doing the code. Don't worry. There is an additional step of classification. So will this be more intensive? Obviously, Krishna, it will be more intensive. It has to be more intensive, right? So for every latitude and longitude, if you see, mm, there might be, let's say, 10 or 12 or 13 houses, right? So the combination of those houses, the median age is 41. Total rooms, sum of rooms in all these houses is 880. Total bedrooms is this much. Population, like how many people living in this particular latitude and longitude in say X or Y house, right? Households. So 126 families, total population is 322. Median income, then median house value, right? So this information we have. We are proceeding to do a data.describe. I'm not going there. We are also doing an info. Everything is fine. Just the total bedroom. I can see some null values, right? If you see. So here total bedroom is having some null values, which we will drop for now. Why? Total bedroom, like the overall data is 20,000, right? Only 207 is having null values. So we can choose to replace it with the median or we can drop. So here for ease of understanding, let's say we will drop it, right? Because we are not doing a session for EDA. We are trying to do machine learning. So let's drop it, right? Now we will be creating some dummy variables. Dummy variable for what? For the housing data. We will be creating the dummy variables. Okay. Where is it? Mm. So once we create the dummy variable, how will it look like? Let me show you first how it looks like. Hold on, where is that OP? I could only see this. Hmm. So now what we are doing is, guys, you can see here, this is the housing data, right? What are we doing while creating the dummies? Why to create dummy? Exactly. So It is a Panda function, a function that performs one-hot encoding. What it does, it converts categorical variables into a series of binary variables, 0 and 1. So where is that categorical population household? Let me see. Yep, here. So what we are doing is mm, 1, 2, 3, 4, 5. Let me not drop this and rerun this. Then I will explain you. Okay. Hmm. Let me rerun this. Runtime run before. So it will run everything before this column. I will show you something. It ran. Now, if I do code housing data dot head, what are you able to see, guys? You are able to see this information. Perfect, no problem, right? How many values are you able to see? 5 values: 1, 2, 3, 4, and 5, right? These 5 values you are able to see. Now, what we are doing is we are asking pandas to create a dummy for us, right? And we are just giving this housing data into it, nothing else. Let's see what it does. I have removed the drop first equals to true. Now, if you see what it does is, what happened? Did I do something wrong? No. Hold on. Control Z. Maybe I removed something or what? Give me a second, guys. For ocean proximity. Yeah, ocean proximity. Where is the ocean proximity? I did not find any such column called ocean proximity. Okay, I get it. So for ocean proximity, I believe they have given some list and which we are adding it here. But maybe by mistake I deleted it. Yes, that would be the reason. Let me get the file again, okay? Because I guess I have deleted that ocean proximity thing. So what I will do is I will upload a new notebook, browse this instructor notebook, this open. What happens? No, like we are just creating a categorical data, just like that, right? So Python won't understand the categorical value. It will only understand numerical. So for that, we are creating dummies. So if the categorical value is, so let's say ocean proximity, where the values are near shore or like far from shore, ocean view, non-ocean view. So for those, we are creating dummy values, right? So that system or Python can understand what is the numeric value against it. That's it. So let me connect it and run the code. Connecting. I'll also upload all the files, all the data sets. Control A, open. Okay. Let me run all. Everything is there. Now I will run all. Obviously, I will get some errors. So where is the error? First error. So this is an Excel file, I believe. Excel SX. I will again run all. So I will be getting some errors. And for housing.this is nothing but a CSV file. CSV housing.csv. Again, I will get some error. Run all. So what I will do is I'm still finding where is that OSINT proximity that we created. So housing data dot drop NA is NA sum. Here we are and here. So before this, I am running it all again, run before against this. And it is a success before run before. And before this, I want to create and see what we have, right? For housing data. So I will write housing data dot head and I can see nothing. Fair enough. Now this one is fine, but I want to see what we do, what we are doing here and what we are doing. That after this, we are getting something else. Here also nothing is happening. I don't know from where that thing came. Maybe we are adding it later. Okay. So these dummy, we will be adding it later. How it happens is I will show you. Suppose along with this data, we had a column along with the housing data, let's say latitude, longitude, house, age. So along with this, we have ocean proximity, right? Mhm. Yeah, ocean proximity, but here they did not use it. So that's why. No problem. I will explain you using this. So let's say latitude is 1, 1, 1, 1, 1, and longitude is 1, 2, 3, 4, 5. So all these are different longitude, right? Let's say house age is 10, 20, 30, 40, and 50. So all these are numeric values, right? Yes, for all categorical values until we mention if we want to do it for only one. So if we don't mention, it will create for all categorical. And if we mention that, okay, we want for this only, then it will create for this. So here, if we mention that we want to create for ocean proximity, so let's say ocean proximity is near or far, medium, near, far, like this. So what it will do is it will create a new column altogether, like ocean proximity near, ocean proximity far, ocean proximity medium, right? So what is the value for the first one? For the first row, what is the value? Let's say first, second, third, fourth, fifth row, right? What is the value? It's near. So what will happen? It will be 1 for near and 0 for these. For second, it is far. So it will be 1 for far and 0 for others. Third one will be like this, then this, and then this. So all the categorical values are now having dummy values. You got it? One hot encoding, this is called. Yeah. Now, if we have this, then what will have? As the number of columns increases, multicollinearity increases, right? What is multicollinearity? Correlation between two feature columns. So our job is to reduce multicollinearity. So in order to do it, what will we do is we will remove any one column. So if we remove this, just by using these two columns, it is still possible for us to determine what is the value of ocean proximity. How? So if here the proximity for far and medium is 0 and 0, it means the value of ocean proximity is what? Near, right? Although one is not present. But since these two are 0, it means the ocean proximity value will be near. Similarly, here it is 1, here it is 1. So as it is 0, it means it will again not be true for these two. It will be true for the near one, which is not present. You got it? Okay, Srina. So in order to avoid multicollinearity, what we do, we try to minimize or reduce the number of columns in picture or in context. So in case of one hot encoding, if you see, we use this concept called drop first. What does drop first means? It means that if the categorical column are having, let's say, three categories. One column is having three categories. Then how many dummy columns will be formed? Three dummy columns will be formed, one, two, and third dummy column. We don't need all three to get to know what is the actual value. We can do that using only two values. How? So suppose here, like if there were three columns, this would have been the exact values, right? But if we only have two, then also we'll be able to identify what is the value, actual value for these three categories. So what are the three categories? Near, far, and medium, right? So if far and medium are 0 and I don't have anything for one, what does it mean? It means that the one that I omitted is having actually one, but it's not there. It's not needed at all for Python. Python will understand that it will by default assign to the third category, which is not present here. Got it? So basically we can do it using n minus 1 columns, right? So that's the reason. What we do is we do this drop first equals to true. Got it? Hmm. Perfect. Now we will prepare the data set. What are we going to do is, for now, From X, what are we doing? From X, we are dropping the median house value and assigning it to, sorry, from house data, we are dropping the median house value. Okay. Let's say the house median house value is our target variable, right? So we are dropping it from housing data and assigning it to X. So all except median house value column are assigned as feature variables and the target variable is Y. What is Y? Median house value. Now what are we doing? We are doing the train test split. Please do it into int 64. Which one? Which one, Vijay? Can you please be more elaborate? What do you want me to do in int 64? Vijay? Okay, you take your time. I'll proceed. So we do the train test split and then we perform k-fold validation in the get dummies code. It's fine. It's all 0, 1, 0, 1. It's not that you won't need 64-bit integers, right? You don't need 64-bit integers. No, you need only 0 and 1. So it's fine. You don't need int 64. Any specific? It is giving ocean 1. No, it should not be the case. If that's the case, then there is something wrong. No, it won't. Here, the housing data would be housing data with ocean. No, we will go there. We will eventually go there. Okay. So here, what is happening, guys? N splits equals to 10. Random state we have taken 42 and shuffle is true. What does this shuffle means? Yes, Avik, yes. We will get to that. I believe that would be present. Somewhere that would be present. If it is not present, you guys can take it as a homework also, right? It's all the same. No problem. What is this shuffle equals to true, guys? Try to make it stratified. No, 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 no. It's not. Shuffle equals to true is not stratified. What else it can be? Yeah, that's just like in class 10th or 12th, you would have randomness. Yes, you would have seen this question in your maths question, a probability question, that four cards are drawn at a random. Uh, and what was the sorry. If a bag is having, let's say, 10 balls of color red, like red, blue, and green, 12 balls, red, blue, and green, each having same number of balls, right? Now, if 5 balls are drawn at random with replacement, what does this replacement means? Once I remove or once I take out a ball, I put it back, right? So the probability that it will be of one particular color is always the same. Why? Because after putting it out, I'm again putting it back before doing the next draw. So here what I'm doing is, here it's similar. I am just shuffling. It's not that it will be serial number wise, like 1 to 1000. So one data, first data set is having data from 1 to 100. No, it will be shuffled, right? So it can vary that the first data, like first row is coming in, let's say 10th data set, right? 10th data subset, it might be the case. So that's what randomness and shuffle, like both go hand in hand. And here we initialize the model as linear regression. Right now we are doing linear regression. We are not doing non-linear, okay? And where is our cross validation score? We have not yet written it or what? Hold on, hold on, hold on, hold on. Where is my cross validation score? Yeah. So guys, see this. From model selection, right? From model selection itself, we are importing train test split and cross validation score, right? So it's not that we need to do something more. We just put our data in cross validation score and it will do the rest. Okay. So that's what I wanted to show you. And here, what we are doing is, please see, Mm, we have the model, we have the X train, Y train, we have the scoring. Okay. We have the scoring as well. And we have cross validation as K fold. So here we have written the K fold cross validation. What is that? It will be number of splits is 10. So guys, tell me how many cross validations it will have. How many k-fold cross validations will it have if the number of splits is 10? So the number of k-fold cross validations is 10. No, 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 it will be 10. It will be 10. How many times it will run? So 10 subsets, it will run 10 times. Now, what will be the number of training sets? The number of training sets will be 9 sets will be in training and 1 subset will be in testing. Okay. So cross validation score, we are putting the model X train, Y train. See, we do not need the X test and Y test here. Why? Because we are creating the model. So everything will be done from X train and Y train. And once the model is created, we'll do final testing or final validation that we will do using X test and Y test. Okay. The scoring, how will I identify that? How will I identify if my model is good or not? So we are taking mean absolute error, MAE. And here we are saying negative mean absolute error. So for scoring, there are like various parameters available in market. Okay. One of them is mean absolute error that we are taking. Cross validation is object we have given here, already discussed this one. And n jobs. Like you can take -1. So -1 is by default, it is -1. If you want 10, it will increase or decrease. So by default, it is -1 only. Okay. So don't worry about it. Now, what we do is the k-fold scores we are getting, right? K-fold scores we are getting. What is the score actually? The score is nothing but this mean absolute error average. So if I will show you. Let's say the number of jobs is 10. I'll do it again. See here what's happening at the end. It keeps running. And now, what is the k-fold score? See, right now the k-fold score is 50,993 something. Now, the score is 2.6 something. So as the number of jobs increases, what happens? This what's happened is this whole process is being done. The one that I've highlighted, you can see the one that I've highlighted. The whole process will run 10 times because CV cross validation k-fold is 10. Now, number of jobs. How many jobs you want for this whole process? Here I have written 10. So this will run actually 100 times. This part will run 100 times. So as a result, what will happen? Virtually, it is getting overfitted, right? If I run it 100 times, what will happen? Like 10 times into 10 times, right? So obviously, it is getting overtrained on a set of data or overfitted on a set of data. That's why either we keep it 0 or by default it's -1, such that the mean, the k-fold scores are not overfitted for trained data. Which is still coming, can't say anything. Okay. So by default, it is -1 only. Now, what is this mean of k-fold scores? So as you know that once I run this, see, you will see something. I will have something for you. What do I get is Control C. This was a tenfold cross validation, right? So these are all the scores for what? These are all the mean absolute error scores for each fold. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now, what we are seeing here, the score that we are seeing is the mean value, mean absolute value. So if you see ABS, absolute value we are seeing, right? The mean of these. So this is my model evaluation that I did, right? After doing the cross validation. So this model evaluation that I did, it is actually on training data only, that how my training data is performing. Then now I trained the model. I also need to evaluate the model. So 2 is good or not. What should be the ideal score? Depends upon the data set. Okay. It depends upon the data set. So with n jobs equals to 10, we are getting less error, and if we put we are getting error 1000. Actually, yes. But you told the process will be repeated k times, so we get 100 k scores. No, 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 no. So basically, it is being repeated 10 times. So 10 jobs are running in parallel actually. Okay. So internally, 10 jobs are running in parallel, but it will give like scores for 10k fold, 10-fold validations only. It's not that it will receive 100 scores. No, will receive 10 scores only. Internally, they will get trained accordingly. Got it, Sheena? So lesser the k-fold scores, better the model performance. Better the model performance on training data, I would say. But again, that trade bias variance trade-off we know, right? We will have to see how it does. But what we can say is, since we are doing cross-fold, like k-fold cross validation, right? We can be relieved that the model will not get overfitted. That much we can be absolutely sure. For that, we need to give one more parameter. I will tell you that. Okay. We need to tell Python that, okay, you are doing cross-fold, k-fold cross validation, but make sure that you don't overfit the model. For that, we have to tell it explicitly. Okay. So before we start to test the model, what's happening? Now the model is prepared. If you see, right? The model is prepared by doing k-fold cross validation and all. My model is prepared. Now what I will do is I will fit the model with X train and Y train and then do the prediction on X test. That's it. So accordingly, I will get a mean squared error for test train, whatever it is, right? So these are the values that I'm getting. Uh, we have already discussed that, nothing. Huh. This is important. Here we are getting a R2 score of 0.65. R2 score or R squared score of 0.65. It means that 65% of the variance is explained by this model, right? It means that still that 35% of the variance is unexplained. So it's not a good model. In order to for it to be a very good model, what we need is we need the R squared to be at least say 90%, at least 88%, 92% like this. So whatever the error is, I can simply say that the model is still underfit. Got it? Can you show the connection between the k-fold score and how it helped? Yes, I will. I will. Sure, sir. So here we have a model, right? What we are doing is using X train and Y train, we are getting k-fold scores on mean absolute error. So after doing k-fold score, our error was this 2.60, right? Now we are using the same model. We don't even need to fit it. Still, we are doing a fit. That's fine. But now we don't need to fit it. Why? Because we have already done this here. So my model is now fit with this X train and Y train in multiple folds. Okay. So now what will I do is if I do this, see, mhm. Oh, are we using Ridge? I did not see that we are using Ridge here. If we are using Ridge, then we'll have to do that only. This is a long data set actually. Let me use it. I will show something more to you. Let me use fit right now. I will show you the cross validation. See, so after we did cross validation, right? We did this cross validation and then again fitted this model and we did the prediction. What happened? The error reduced, right? See, the MSE and R squared is still 0.67, 67% of variance explained, but this reduced. Now I will show you something. I will block this, okay? I will block this. I will say that, okay, I don't want any k-fold to work. And as a result, sorry, and as a result, my model will only get fit normally and predicted normally, okay? So what I will do is just model linear regression. I will call it again. Okay, see, I'm again calling the model. So the model is now blank. I am not applying this a-fold. So no cross validation scores, nothing. No cross validation is happening. And I'm directly fitting and predicting the model. And let's see how it gives the result. It's almost the same because the data set is like that. So it's not complex data set maybe, but generally it will be more. Okay. So if we are using cross validation score to train the model, what happens is these errors get reduced. But since the data set is maybe very linear, so here even if we are introducing the cross validation, it's not actually of any benefit because data is too linear. Simple. Okay. But you understood the concept, right? Model in the below. No, this one we are not using. Even if we are refitting it, the model here was already trained in cross validation. So here, if you see the model was empty, right? It was empty. Here we have already used cross validation score. So the model is having the information about this cross validation k-fold, X train, Y train. Here we are just giving it the data. No problem. Okay, hold on. Hold on. Sahar is saying one doubt. Can you show the correlation? It is already fit. Yes, I got confused. You already fit using k-fold, then again fit. So I thought k-fold works. I will unmute. But we are not using k-fold model in below. What I will do now is since it is getting confused, I will show how it works in tandem so that we are getting same result because it's very linear data. I will show you how both it works in tandem, right? So that will be better. Like without even using fit, how to do it, right? So that will work. Model instead of using existing model. Shiva, on this question I did not understand. Wait, so the updated parameter using K4, yes. Who is saying unmute? Wait, I will unmute you. Participants Unmute. I got your confusion, guys. You are not able to understand this cross validation and fit. So if you have already used cross validation, why we are using fit and all, right? Okay, I
Yep.
got it.
Sorry. Thanks for unmuting. I think all of us are talking the same thing, different language maybe. But only question is, see, this model generally when we fit, the parameters get updated, right? Say X, Y, Z of the I mean A, B, C parameters of the linear value gets updated, right? So basic question is, when we do the cross validation, I mean cross fitting, the values get updated, right? And on top of it, again when we fit, there will be another one regression happening. And but you are saying that old parameter value will not be lost. Is that right?
I You got it. Yes.
Okay, so what do you mean? Even if you fit it, it is going to be another one revision. Nothing going to hurt it. Correct?
The parameters are already set on it, right? Even if
Uh-huh.
you are fitting it again, it is like it is getting new data.
So it is not going to erase and do the fit again, right?
No, it's not going to refit. It is going
Okay,
to like append or something like that. Okay, I will show you. I got
okay,
your
okay,
point.
okay.
I will show you something. Okay, how both works in tandem. How only one can work. How only k-fold cross validation will work. How only fit will work, and how both will work together. Okay, let
Right.
me show you. That I guess will like resolve all the confusion. Model is empty in linear regression. Yes. Who is this? Siva. Right. So here, whatever we are using, right here, it is empty, and in this cross validation, what are we doing? We are saying k-fold cross validation I want to use. So here I am basically splitting the train and white train into 10 sets and training the data. Here I have not mentioned anything, but you can see I have put it in cross validation function, score function. So here it is internally fitting the data multiple times. And after that, I am doing this fit one more time. That's it. You got it? No problem. Let me do it for you. Oh, it's already 9. Let's go on a short break. And once you come back, I will show it to you. Okay. How this cross validation and this works in tandem. And then only for on the same data set, I will try to show you. Even a small difference, I will make sure I do. Okay. Such that like cross validation, only fit and cross validation and fit together. I will try to show even 0.01% of change, but I will. Is that second fitting needed? It is. Because without fit, you cannot do predict. It is needed. Dinner break? Okay, you guys do dinner. No problem. Take 25 minutes. Since it's already 9, I'm not going to take any 5 minutes breather later. So take 25-minute break, guys. Okay. Before that, let me launch the poll. Yeah, guys. I will show you. Sir. It is compulsory. So it will be blank fit. I will not fit anything. I will just use fit, but it will be blank. I will show you. It's interesting. Don't worry. Okay. Yes. You will like it. No break. I was waiting for the poll. You can see the results, guys. I'm opening the timer. Uh, Someone is saying reduce the pace. Someone is saying I need to give more examples. Guys, is the pace really high? I'm taking it so slow. Yeah, from the example point of view, so many examples are lined up. See, we will get examples, but yeah, we need to also understand the concepts, right? Apart from that, it's fine. Okay. Let me give the timer. Okay, guys, you are able to see my screen? Let me put my system in charge. You are able to see my screen. Okay, so please confirm that you are able to hear me and see my screen. Yeah, okay. So let's do this once again. Okay, here the first case. What is the first case? The first case is we will be using. Hold on. The first case is we will be using only dot fit. Okay, so without k fold, what we are going to do is we are directly going to at runtime run before it is running. Yeah, I will now run this as well. And what is my test score? See, you see what is my test MSE? If I am just using dot fit, okay, and the R squared is 64% of variance explained. Okay, I just use dot fit here. Now let us use both of them together. So here what I'm doing, I am just using both of them together. This one is not needed. Here I'm just finding one value, right? So not needed. Here I will do is I will do run before again. It's running till this point ran, and I will run it again. Okay. Why it's giving the same value? Something is wrong. Maybe even if I'm running it again, something is wrong. Some problem with the data, it seems. Anyways, so what I wanted to show you guys, I told you that we can also do it without using fit. How can we do it? Here, this cross validation that you can see, right? It itself does the fitting and testing. Okay, fit and predict it does by itself. How? I'll show you. So I will write one line of code where I will say instead of x train and y train, what I will do, I will pass the complete x and y data. Okay, I will remove the scoring part. I don't want any scoring. I want it to do predictions. So here it will do just predictions. I'm giving it x and y. It will train the model on, let's say, 9 subsets and will do the prediction on one subset. Okay, and this it will repeat for multiple times. So now I have the prediction. What can I do is, let me run it. Yeah, it ran. What can I do is in the next line, I can say mean absolute error, and I can pass y and predictions. Okay, so y is the actual value and prediction is the predicted value, right? And here I can get the answer. What happened? Inconsistent number of samples. Huh? I will need to fix that. So what can we do is n jobs I can remove. Model is there, this and this, mean absolute error. Yeah. Mean absolute error, y and prediction. It should give the value. What is the problem? Found input variables with inconsistent number of samples. The why? What is the prediction value? Why I can understand. And what is the prediction? Let me see. The prediction is like this. So it's giving me 10 predictions. So 10 y should be there, right? And in cross validation, k-fold, what we are doing cross validation, I'm passing the oh, passing the model. Okay, that's the problem. I do not need to pass the value here at all. I do not. prediction is equals to cross validation. Okay, that's where I made the mistake. Instead of cross validation score, I need to use cross validation predict. Okay, and here I can simply call one thing. Uh-oh, it will give error. And here I can simply call from sklearn dot model selection import kfold comma cross validation, not scores, cross validation predict. Okay. Now, once I do the prediction, what it will do is, uh, what happened? Cross validation predict PREDICT. What is the error? If your import is failing due to missing package, you can import pip. Cannot import name cross validation. Oh, sorry, cross CROSS. I got the answer. Now, see, the prediction will be for multiple rows, right? Now I can go ahead and do the mean absolute error and I got a value. Got it? So this is just for cross validation thing. Okay. Yeah. So this is just for cross validation. You got it? Someone was asking, no, if we don't use fit and predict, how can you do? You don't need to. You just train your data on whole of the model, like whole of the data X and Y, and then ask it to predict. What it will do? It will do both. It will train and test and predict. That's one. Number two is uh, only fit and predict. And number three is first cross validation, then fit and then predict. Yeah. 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 Like somehow this, if we are doing with cross validation, no, somehow it's not working. I'm not sure why. I will need some time to look into the code and see the values. It should have worked. So this one is just, this one was just predict. Now I will also this one. Okay. So what happens is, guys, you were asking that after doing this cross validation, right? Why are we again doing this fit, right? So the answer is very simple, right? That in cross validation, what we are doing, please repeat again for more clarity. Which one exactly? Which one exactly? Okay, fold here, please. Okay, I will do it for more clarity. No worries. Okay. Did you guys understand just the cross validation predict? Yes or no? You want me to repeat it again? Repeat it. Okay. So what we are doing is, instead, whenever we did cross validation score, what happened? The model got trained on X train and Y train data across multiple K folds, and then after the model was trained on sample data, we retrained the model on overall data and then predicted using it. So this was the combination of cross validation, comma, fit, comma, predict. Okay. First, the model is trained using k-fold cross validation on sample data. Then the model was fit on whole data set, right? It means whole of the trained data set. And then it was predicted on the tested data set. So this combination is clear. Yes, it is clear how it was done. Yes, guys. Please confirm if this particular line is clear or not, what we did. Any questions? Do ask. What is wrong? Wrong. Cross validation score fit model predict. Cross validation score. Are we in predict? Okay. So here what is happening in cross validation? Here we were using cross validation score. Okay. Depending upon the depending upon the score, we were training the model to get the minimum possible score, right? After that, we were fitting the model on the entire trained data set and then predicting using the test data set. Yeah, I'm recapping. So this recap you understood, Vijay? No? Okay. Cross validation method you understood, right? Everyone? Okay, got it. Got it. Okay, let's do it from here. What we are doing is cross validation score we are doing. We are giving the blank model. We are giving the X train and Y train, and we are asking to perform the cross validation on negative mean absolute error. So mean absolute error, we are asking to perform the cross validation to find, let's say, 10 iterations will happen, right? 10-fold cross validation will happen. So for each cross validation, we will find a best mean absolute error. So overall 10 mean absolute error we will find. And as a result, my model will get trained, right? Once my model get trained, what happens is we go ahead and then fit the model on entire data set. What is the next step? Next step is fit the model on entire data set. Better let me write it for you. Yeah, better let me write it for you, how we do it. Let me know once you are able to see the screen. So what we do is explanation. First is k-fold cross validation. What we do is split data set into 10 parts, right? Train model on 9-fold and test on 10th. Repeat the process 10 times. So for 10 times, we will have 10 mean absolute error. Calculate mean absolute error, mean of mean absolute error, right? Till this much. After doing this, what happens? We get my model is trained using cross validation, right? After that, the second point is training on full data. How training is done on full data? Model dot fit. Okay, model dot fit. X comma y. If you want, you can also give model dot fit x train comma y train. Okay, both works fine. And what is the third one? Making prediction using model dot predict, and we will provide x test there, and it will do y predict equals to this. Once y prediction is there, what is the fourth step? Find error. So mean absolute error equals to MAE. Inside I will give y actual comma y predicted. So whatever is the difference between them is the mean absolute error. Got it? Everyone got this step or not? This is the combination of all three. Vijay, let's go sequentially. Yeah, we will cover all three here in this tab only. It is clear till one what we are doing. The combination of cross validation, training full data, and then making prediction. Where is from y actual? Y actual is nothing but this y actual value, and this y predicted that we are getting from model dot predict. Okay. Now, what is the generic? The generic method is model dot fit on x train and y train, right? And using this model dot predict on x test, right? We will get y predicted equals to this, and again find the error as mean absolute error at y actual minus y comma, sorry, not minus, y predicted, right? This is the generic method that we do if there is no cross validation, right? Now the third approach is only cross validation. In this case, in the first case, for k-fold cross validation, what we used was we used cross validation score. Okay, when we are only using cross validation, no fit, no predict, what we are using is cross validation predict. What we will do is we will say cross validation predict. We will give the model. Okay, we will give the x and the y data, full x and y data we will give. Okay, and then CV equals to k-fold, where k-fold is nothing but k-fold cross validation, and we will give the values like n split equals to 10 dot 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 whatever it is, right? So using this, what will happen? We will get is y directly. We will get y predicted. Okay, from cross validation predict. If we give model x value, y value, and the CV equals to k-fold cross validation, where k-fold cross validation is this, we will directly get the predicted value, and then we can go ahead and find the error. Mean absolute error equals to y actual comma y predicted. So these are the three different ways in which you can go ahead and do your work. It is clear now? Much clear, guys? Everyone, please comment if it is clear now. Now let's see the same in code. Shall we? Shall we see the same in code? Everyone. On code, same understanding requires. Yes, let's do it. So first statement, what was the first case? The first case was we will use both cross validation and fit predict. Okay. See, cross validation score, we are giving model, we are giving X train and Y train, and we are asking the model to score on based of mean absolute error. We are giving this cross validation as k-fold and job whatever you give. What is k-fold here? K-fold is n splits as 10. Okay. Now, when we train the data on k-fold cross validation, after that, what we do? We find the average and all this happening, right? Here, if you see, we are finding the average. Where is it? We are finding the average and all, right? After that, what's happening? We fit the model on, whole of the data. Here we are taking train data. Fine. I already mentioned, right? Does not matter you take whole data or train data. We work with train data right now. Now we do predict, and after that we do mean squared error. Okay, this is the first case. What would be the second case? The second case would be just this. Do not go for cross validation. So their cross validation would be commented. So like this would be, it would be commented like this, right? So no cross validation would be there. Just fit and predict. That is the second case. So, and the third case would be no fit and predict, just cross validation. This one, the one that I have commented out, just this one, just 3 lines. What we are doing is we are importing k-fold and cross validation predict. In this case, we are using only cross validation predict, not cross validation score. What we are saying is cross validation, aap hi mai baap ho. You do everything. After you, I don't want to do any prediction. So cross validation is like k-fold is doing the prediction for me. So for that, they have a different function called cross validation predict. I'm using it. When I'm using the cross validation predict, I'm saying I will give the empty model, and X and Y I am giving, and then I'm giving the CV as KF k-fold cross validation, where KF is the same and splits is 10, right? And then when it's happening, I am getting the prediction value, right? So what is the prediction value? Like we have an actual value, Y actual, I am getting Y predicted. So accordingly, I can go ahead and find the mean absolute error. So this is my mean absolute error. Okay. So what do you think? In which case it will give me better result? What do you think? Case one, where we are using all three: cross validation, fit, predict. Case two, only fit and predict. And case three, only CV. Which one should give me better result? Actually, case one should give you better result, but there is also a probability that this will do the overfitting, right? So we don't know which case will give us better result. It's all on trial and error. We'll have to do trial and error, right? So while you are building a model, not testing, while you are testing also, when you are building and testing a model, all you need to do is see which one is having the minimum error. Guys, this part is understood properly. Okay, if that's the case, then we will study regularization now. Understood, guys? Till now, everything is clear? Give a quick confirmation. Perfect. If that's the case, why it's not getting charged? Oh, it's not getting charged because it's not at all connected. Now it's getting charged. Now, we talked about improving the model's performance. But can you imagine, or like, can you imagine that this can be a case that while in trying to improve the performance of the model, we might actually overfit the model during its training? You agree, everyone? Right? So what we need to do is we need to basically, the question was raised before. Which one? Overfitting. Obviously, it was raised before. Unmute. So everything has a sequence, right? Okay, sir. Let me unmute you. Everything has a sequence. Yeah, I unmuted you.
No, I think somebody previously raised the question that if we do regression, I mean iteration, will that not overfit? But what we understood, like if we take a different model which exactly suits the data, that time only it will overfit, right? But now again, you are saying when we do this regression or like when we
I
fit.
will answer your question. I will answer your question. If we are taking X train and Y train,
Mhm.
okay, there is no X test and Y test. If we are taking X train and Y train, and that X test and Y test that we have are totally different, okay,
Mhm.
then whatever you do, the model is going to get overfit. You got it right. For example, say in X train and Y train, you have apple, oranges, But in somehow in Y train, sorry, X test and Y test, you have grapes and pineapples. Now you tell me, whatever model you create, it is going to get overfit.
But one question here again, this doesn't mean it should be overfit, right? See, for example, there is apple and orange in your train. Okay, we are designing a linear regression, say for example, and it's not a overfit and it's a straight line. Let's give I'm just thinking, and but
No.
you give a train test data which is totally out of the scenario, then
Yeah.
it doesn't mean the model which we designed is overfit. Maybe it is like we are trying to test a
No.
elephant with a
Yes,
fish,
yes.
right?
So that for that we'll need to see if R score is what is the value of R score, right? In order to get to understand if it is overfit or underfit. That's a different point. Consider, okay, I should have mentioned this also. Now consider that we have R score in our hand, right? We have R square in our hand. Now we are seeing that the model that we have developed now explains 99% of the variance. Okay, let us take some assumptions. Then we will come to regularization. It explains 99% of the variance, and the training error is very low. Mind you, the training error, that is mean absolute error, you can say, is very low. So in that case, what will we do?
Okay.
We will go ahead and try to retrain the model such that the training error is low, but the R squared is not 99%. Let's say it's 95% now. We will try to get that, achieve that. But consider a point, the data set is such a whatever it is, we are not able to achieve that from using cross validation. Okay.
Mhm.
In that case, we will have to have some tool in order to ensure that we reduce overfitting. That's number one. Number two is whenever we are learning something, we first learn its pros, then we learn its cons, right? Its cons. It's not that when you are learning something, we will learn, okay, this method, this process cannot do this. No, we will learn what it can do. So yes, it can manage overfitting, but it's not that it will minimize overfitting. No, that's not the case everywhere. So for controlling overfitting, we have a different process altogether. That process is called regularization. Now you get it?
Okay, so your point is after we do all the preliminary kind of test training and we have things like the R square and thing, now you are talking about this point, right? Okay.
Yes. Now further, we like cross validation has like said, okay, that is the max I can do. I cannot do more. Then what? Then also like it looks like no, my data is looks overfitted. Since R squared is 100% or 99%, 100% of the cases it is overfitted, right? Because you have to leave some room for unseen
generic
generic data. So in that case, what will we do is we will use a technique called regularization. What
and,
regularization?
and one question, this overfitting we can find it out only through the graph by viewing it, or like this R score will tell us?
R square directly tells us. If R square is greater than 95, blindly you
Overfit.
can say that it's overfit. If it is less than say 85, you can not 85. If it's less than let's say 80, you can say it's underfit. So the region between 80 to 95 is the perfect fit. Now in that, again you will like here we don't have one thing. We will cover it later actually. Once you do the prediction, you remember right that overfitting and underfitting is on training data, and the variance that we calculate is on the testing data.
Correct.
So we also need to see variance. What is the value of variance? Then we need to get the bias variance thing from the graph. We do a lot of things, and yeah. So far we are just understanding and learning the tools that we have. Now, how to use all these tools together? For that we have a project. You got it? It's
Got it.
not that whatever we have learned so far, we will use everything in one data set. No, that can't be possible because if we do that, time is not going to permit us to do that. So we are learning all the tools that we will need separately, and we will do 2 or 3 projects to understand how to use the tool, when to use the tool, how to use the tools together, which tools not to use together. We are going to learn everything. Clear?
Yeah. Okay. Sure.
Okay.
Thanks.
Now regularization. Regular. What it does? The basic thing is it minimizes or it addresses the issue of overfitting. Now, how it does the overfitting is, how it minimizes the overfitting is, it first identifies, guys, I am pointing few things. Okay, let me share my screen and let you explain it. How regularization on a generic context on a generic context, what it does is, suppose there are 4 feature variables. Let's say we are in the medical data set. 4 columns are age, BMI, smoking, lifestyle. Let's say these are 4 values. Okay. Now, what is the final target value? Target value is premium. My system or my regularization system will find because of which particular column, or which particular feature variable, this output premium is getting overfitted. It's not that because of all the columns it will get overfitted. No. So let's say the data is such, the distribution of data is such that because of BMI and age, it is getting overfitted. So what it will do? There are 2 scenarios. What are the 2 scenarios? The solution is one only. The solution one, and inside that one solution, there are 2 different scenarios. These columns, which are being the reason primary accused for being overfitted, penalize them. How to penalize them? How to penalize them? Reduce their weight is the first case, and nullify the weight is the second case. So in the first scenario or in the first solution, if BMI and age are the reasons for being overfitted, reduce the weightage. For example, if earlier the BMI was, let's say, X multiplied by BMI plus, sorry, X1 multiplied by BMI plus X2 into age, now we can update it to 0.5. Sorry. Now we can modify to 0.5 times X1 dot BMI plus 0.4 times X2 dot age. So this is how we are penalizing the columns or penalizing the feature variables, right? The another way is to nullify them at all. So how to nullify them? BMI, I removed. I just keep the age, right? I just keep the age. So these are the 2 ways I can nullify, will remove them from the picture, right? Yeah. This is on a generic context I am saying, okay? It's not like this. This is the first step, baby step to understand regularization. Now we will move deep into it. But on a high level, these are the 2 ways. You understood? Yes or no? You understood? So suppose we nullified this. This is one way. Like in one scenario, this is one way. What is another scenario? Another scenario is, suppose there are 4 columns which are collinear. In one case, what will happen? I will choose only one column. I will proceed with only one column, right? 3 columns will be removed, because why use 4 columns when they are collinear? Got it? Only one column will be used. In the second case, all 4 will be used. Just that weight will be distributed, okay, among the 4. So eventually we are using maybe one only, but we are distributing the weight among those 4s depending upon their percentage of collinearity. So these 4 aspects you understood. Now we will go deep into L1 and L2 regularization, which is a combination of these 4. You understood these four scenarios separately, right? Now we will go deep and understand what L1 and L2 regularization means, which is actually combination of these four. Everyone, please repeat fourth scenario. This one, right? This scenario. Prashant? Hmm. Suppose four columns are collinear. In one scenario, we use only one column for result, like providing the result. Why? Because whatever this one column says, the other three will follow. So even if we use one column for the report analysis or for target variable analysis, variable analysis, it's fine. In the second case, what we are doing is, let's say the four columns are x1, x2, x3, x4. So instead of only using x1 to find its target, its relationship with y, what we are doing is, we are saying, okay, let's use 0.3x1 plus 0.4x2 plus 0.2x3 plus 0.1x4 to find this relationship with y. This. So what is happening? Weights are distributed. So all of them, since they are collinear, right? All of them are used depending upon their percentage of collinearity with each other. Understood, Prashant? Understood? Yeah. Now we will proceed to understand L1 and L2 regularization. So basically, now you can create a note for this, okay? Because this is very important. So I will say, create a note for it. Write along with me. That will be better for you. Now, whatever we discuss those four scenarios, it will be similar to that. Let's get to understand this, okay? Regularization, what it does, prevents overfitting by adding what? A penalty term to loss function. Now, two most common types are L1 and L2 regularization. This is called, L1 is known as lasso and L2 is known as ridge. Ridge regularization. Sorry, ridge regression. Lasso regression and ridge regression, L1 and L2 regularization. Okay. Now, what L1 does is, L1 or lasso. What happened? Oh God. What happened? From where? What is running, man? I have no idea what's running. Let me remove all the tabs. I have removed all the tabs, no? What is left? Can you comment which music was it, guys? Anyone? Hmm. I will come to that. I'll come to that. Oh, what is that? Everything got deleted. When we add penalty to the loss function, will it not impact all the bits instead of particular access parameter? That is what we are going to learn. That is what we are going to learn. This is a generic comment, right? So I hope you have written already. Regularization helps prevent overfitting. What was that? By adding a penalty term to the loss function. This much is fine. So we will start with L1 or lasso. The technique is adds absolute values of coefficient as a penalty. The equation is how the loss looks like. The loss looks like summation of y minus y average square. This is y, that is predicted value, minus y average square plus lambda into summation of the coefficient. This is lambda, which is the penalty that is added to the coefficient. So what is the technique? Adds absolute value of coefficient as a penalty. So this bar I am taking is coefficient. Right? Sorry, this bar or mod I am taking is for absolute value. Lambda is the penalty that is being added, and this is the coefficient. Okay. Now, which is what value? Y is equals to actual value. Y bar is okay. This one, it's not bar, it's cap. Y cap is predicted value. Bj or Bi, whatever you say, is coefficient. Now, what is coefficient? It's like y equals to beta 0 plus beta 1 x plus beta 2 x square. So beta 1, beta 0, beta 2, they are coefficients, right? And lambda is equals to regularization strength, right? Lambda higher means stronger penalty. Okay, higher lambda means higher penalty. Got it? So using this, what happens? What is the effect? If we use this formula, what is the effect? Effect is nothing but effect is in feature selection. How? Shrinks some coefficient to exactly 0, removing unimportant features. Okay, so if lambda is such, that it is moving the coefficient like lambda into bi or something, right? So b1, b2, b3, whatever it is, it moves to 0 exactly. So what will happen? The unimportant features will be removed. When does it helps? It helps when only a few features are important. Okay, what are the use cases? Like we are really keen in understanding what is the use case. Saha is saying something. Hold on. Oh God, I was not even saying. Oh, thanks, Saha. Okay, we start from here. I will repeat. Okay, guys. Since how long you were not able to see? Let's screen. Request you to share. Oh God. Oh God. 2012. So 8 minutes. You were not able to see anything. Oh God. Yeah, yeah. Whole stuff. I will explain. No worries. That's very bad, huh? Okay. So everything we will break it down into few pieces. Yeah, yeah. Like Saha actually did a great thing. I don't know how he did it. I don't know how he had that access. He actually, yeah, he asked for screen share, so it actually came out as a pop-up. So when I'm explaining, no, I'm not actually looking at like whole screen comes up, no, so I'm not able to look at the chat. So because everything is clear, so since I'm explaining, I thought let me explain the whole topic and then see the chat box. So as Saha asked for the screen share, it like gave a pop-up, so I got to know. Okay, no problem. Let's see. L1 or lasso regression, L1 regularization or lasso regression. First, let us understand what is the technique. The technique is it adds absolute value of coefficient as a penalty. Okay. So what is the mean squared error or mean absolute error, whatever we call it? Y minus Y predicted. Y actual minus Y predicted is my error term, right? It's square. What we do is, whenever there is a overfitting case, we penalize the coefficient. For example, let's say this is the case. Y equals to beta 0 plus beta 1 x1 plus beta 2 x2, right? Like this. So what happens is beta 0, beta 1, and beta 2 are my what? Coefficients. So whenever there is a case of overfitting, we penalize the coefficient. And this is the overall equation where loss is equals to summation of y minus y predicted, like y actual minus y predicted square, plus lambda into summation of coefficients. That's it. Okay. Lambda into summation of coefficient. Now, if you want, you can take this square. If you don't want, you don't take this square. No problem. Okay. We are not concerned with this part. We are concerned with this blue part. Okay. Where this is our main thing. Our main aim is to minimize this B coefficient. Okay. Now, what is this? Y is the actual, Y bar is the predicted value, Bi or beta I is the coefficient, and lambda is the regularization strength. Higher the lambda value, stronger the penalty, right? Higher the lambda value, stronger the penalty. Now, what will happen is, as a result of that, what will happen is some of the features or some of the coefficients beta, right? Beta I, whatever it can be, it shrinks some coefficient to exactly 0. This is the first scenario. For L1, what it does, it shrinks the coefficient Bi to 0. Okay. So if some of the coefficient are shrinked to exactly 0, what will happen? The unimportant features will be removed. The unimportant features will be removed. And how it helps? And when it helps only when only a few features are important. For example, suppose in a column where there are, in a data set where there are 100 columns, but only say 5 features are important. So what you do? In order to avoid overfitting, what you do is you like create the regularization such that 95 of the parameters or feature variables turns to 0. The coefficient turns to 0 such that you will have only 5 feature variables. No. It will. But how we know it removes only unimportant? Because it identifies, the process is such that it identifies which are the parameters because of which the overfitting is being created, right? So it only removes those. Sorry. So which are the parameters where overfitting is being created? It penalizes those, and as a result, while penalizing, some of the parameters or some of the coefficients shrinks to 0. So eventually, only those coefficients shrinks to 0 which are not important. Now, if suppose a model was trained on 100 parameters and now a model is trained on 5 parameters, which do you think will be less overfitted? Obviously, the model trained on 5 parameters. It's not. It's statistics. It's stats that is beyond our scope. PhD level research they do, and everything is being now put into code. So we are just going to, we don't even need to use that code. We are just going to use that function in which the code is written. Okay, Shaha? Okay. Yeah. So now, effect we got. Now we will understand the use case. What is the use case, guys? We keep asking for use cases. So let's try to include use cases as well. First use case is sparse feature selection. For example, if we want to perform, let's say, text classification, right? Or gene selection in bioinformatics. So in this case, what happens? Like where use case is where feature selection is sparse, right? In text classification, not every text is a keyword. Only few texts are keyword. Others are stop words or something, right? Which are not mandatory. Similarly, in gene selection, no, gene selection, leave it. I will not make you understand. Many of you don't know about biology and all. So I will try to sum up it like this. It works well when only a few variables affect the output. Okay. So finally, if 100 columns are there and only 5 affect output, If we are taking all 100 into consideration, that's a bad thing. So what we do, we implement L1 regularization, and it reduces the number of columns to 5. Why? Because all other 95, the coefficient are reduced to 0. This is seeming very complex. The better way is to find the correlation. I will tell you the better way. To find the correlation of each column, because I'm coming to you, okay? To find the correlation of each feature column with the target variable and arrange it in descending order, and then take top 5 columns. Done. Isn't it interesting, guys? Do you agree? This method. So here no regularization is needed. You understood? You did not? Let's answer Vikas's question. What if statistically a feature gets removed, but as for domain knowledge, it is an important one? That's a nice question. What was the last statement? Oh God, Vijay. Someone will have to tell me. I forgot what was the last statement. Someone please tell me. In the meantime, let me try to answer Vikas. That's a really great question. But as per domain knowledge, it is an important one. See, it is important to me, right? Or it is important to the person who is developing that algorithm. Fair enough. Keep a separate copy to see how it behaves. But for the model, if it is unimportant, it's of no purpose to the model, right? So for yourself, you can keep a separate copy so that you can review. But for the model, if it is statistically unimportant, it's unimportant, right? To the model, domain knowledge is nothing. It's all about information, relevant information to it. So, Vijay, what was my last statement? Guys, what was my last statement before I answered this question? What was my last statement, guys? No, 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 no. It's not the data is wrong. It happens. For example, 1 second. Data wrong as in for our model training, the data is not a, that I agree. You said something 90 to 95, 90 to 95. Got it. So if there are 100 columns in a data set and only 5 are important, right? So we use L1 regularization to reduce the other 95 columns to 0. Fair enough. What can we do? It is, if there are 100 columns, I will say 99 are feature columns and 1 is target, right? Find correlation of these 99 feature columns with the target column. So you will have 99 correlation values, sort in descending order, right? So let's say column 5, column 10, column 15, column 20, and column 25. These are the 5 columns which are having highest correlation with target value. So what will we do? We will, since we have sorted in descending order, we will take these top 5 values and start working. So in that case, this whole L1 regularization is not at all needed. Is this concept you understood, guys? This concept we are going to study as PCA and LDA, principal component analysis and linear discriminant analysis we will study. Okay. Now, lasso regression is done. Now, let's see what ridge regression or L2 regularization means. Ridge regression or L2 regularization. Here also, we will study in various pointers. So what is the technique? The technique is, in L1 regularization, we were adding the coefficient as a penalty, right? Here we are adding, what happened? Adds the squared value of coefficient. okay, as a penalty. Okay. What is the formulation? Mathematical formulation? It is nothing but loss equals to summation of y minus y cap whole square plus lambda into summation of beta I square. So instead of just beta, now it's beta I square. Now, because of this, since it's square, right? Since it's square, what's the effect is does not eliminate features, but swings to 0. What happened? Okay. So in this case, none of the parameters gets eliminated. Not 2 0 towards what's I'm writing. Hold on. Huh? It's not 2 0, it's towards 0. So they are not 0, just very, very, very small. What it does is it prefers smaller weight, but it keeps all features. And this works well. All features contribute to prediction. Okay. So consider a case where your model is getting overfitted because all the parameters are involved in prediction. But that can be true actually, that exactly all parameters are involved, right? Then how to remove the overfitting? So in that case, we use a ridge regression. What it does for overfitting values, what it does is it penalizes the squared value of the coefficient, right? The effect is it does not eliminate the features, but it shrinks them to towards 0 such that their weightage is very low. So as a result, what happens? All the parameters are preferred, just that their weightage reduces. So since all the parameters, most of the parameters which are like not important or less important, so as to say, they will still be there, but their contribution or their effect will decrease, right? So this technique basically prefers smaller weights, but it keeps all features. Works well when all features contribute to prediction. Okay. Now, what is the use case? Used in high dimensional data set where all features carry some info. Okay. And it is preferred when high correlation between features. So here what happens? If there is multicollinearity, all the columns will be present just like their weightages will be distributed. So at the beginning itself, we studied 4 scenarios. So L1 and L2 regularization or lasso and rigid regression is a combination of those 4, right? Now, there is a, let's form a table since you guys are already making notes. Let's find the key differences. What are they? The feature. L1, L1 and L2. No help required, no help required. Okay. What happens here in feature selection? Feature selection is true. Feature selection means which are the feature columns which we want to use to predict the output. So if there are 100 feature variables, we need to perform feature selection to say reduce it to 10 or 5 columns, which will be influential in predicting the target value or the output. So feature selection is yes here. What happens is other weights become 0. And what in case of feature selection in case of L2 is no, because all the columns all the columns contribute to the target variable prediction, right? Multicollinearity, it is not handled well. Why? Because if there are items with like multiple columns with collinearity, what happens? It does not handle them. It basically removes them from the picture. So if 4 columns are having collinearity, it removes 3 and only uses 1. So it's not handling them. It's eliminating multicollinearity. So it's not handling. But in L2, yes, it handles multicollinearity. How? If they are multicollinear, then the weights are distributed among them now, such that the adverse effect that they were having, right, because of collinearity, now because of the reduced weights, that adverse impact of collinearity is nullified. Okay, and this works best when the feature columns, few important features, and L2 works best when all the features contribute. Guys, please tell me, this L1 and L2 regression is clear or not? Now, Gandhiti is asking, but did we not discuss where there is high collinearity, better to eliminate columns and keep only one of them? All of them have similar impact on target value. Similar and same impact are two different things. Suppose they have similar impact, but there can be two scenarios or two ways to handle them. What? One, only take one, don't take others. Number two, take all, just to reduce the weight. So in second case, what happens? We keep the essence and the flavor of all the columns together, still reducing the overfit. In one, we are reducing in L1 regression, we are reducing the overfit, but and in that process, we are losing out on some like columns of data, right? It's not that they will be 100% similar. They might be 90% collinear or something. So still some part of data we are losing, which could have been important like that, right? So yeah. So, okay. Guys, sir, please help us to get these iPad notes downloaded and in the chat or already reference. Yes, sure. Everything is there in only one sheet. See, I have not even used a different sheet since we started. Everything is in the same sheet. Don't worry. Okay. So whole machine learning PDF will only one sheet. Okay, Vijay. So that if there are multiple sheets, multiple downloads, you will fade away. It will fade away. So only one sheet, one download. You need it now. Okay. Let me save it, then share it. Share. Print. Fair enough. Creating PDF, and I'll do a airdrop real quick. I go here. Done. Now let me share it with you. I hope I will be able to download it. If not, oh, sent received. I will rename it as ML Notes. What is the date today? The date today is 15th Feb. 5.6 MB. I hope it will get downloaded. EngageX. EngageX session materials. Login. If classes. Session materials. Add session materials. I will add as of today's class, 3rd. I will try to insert Oh, sorry. Downloads. This not open. Got uploaded. Great. Please check, guys. You are able to see this or not. If not, I hope you'll be able to see it for sure. Yeah, guys, you are able to see. Everyone, please confirm once. Okay, awesome. Let me see if we can cover the rest today. Regularization we cleaned, Lasso we did. Oh, these are a bit more complex formulas, so I did not touch this. Okay, but yeah, all in all, we did everything. And instead of alpha, it's lambda, what we covered. Okay. Data set wise, we will do it tomorrow. So only Lasso and rigid implementation and grid search and random search remains here. That we will cover in 1 hour tomorrow, and then we will cover the 4.1, 2, and 3. Done. All good, guys, then. Okay. So Anish, you're there. You can share the feedback link, please.
Yes, sir.